Hi, good evening. My name is Stephen Benjamin, and I'm going to be demonstrating my final project for CSCI E-93 computer architecture. This is the SKB instruction set. My architecture is 16 bits. It has a register array with 8 registers. There's an additional stack pointer register that has dedicated pop and push instructions, and of course as well as the PC and IR registers. Memory is word addressable only. I have no unsigned instructions. This means that both offsets and immediates are always sign extended. And there's no branch instructions. Instead of this, I use skips. So skip on equal, skip on not equal, skip on less than. When these conditions are true, the PC gets incremented by 2. So you'd implement a branch by writing a skip instruction immediately followed by a jump instruction. And my special feature is a load feedback shift register, which I'll discuss shortly. The register array has 2 special registers, 0, which always returns 0 and discards writes, and the RA register, which contains the return address from a jump or jump register instruction. And by convention only, the registers have names that allow you to write your programs a little bit easier. So A0 and A1 are used for arguments to a subroutine. T0 and T1 are considered temporary value storage. S0 is a saved value. So if your program is a good citizen in my instruction set, you'll make sure to save and restore this value when entering and exiting a subroutine, and V0 contains a return value. There's 3 kinds of instructions: R-type, I-type, and J-type. Register type instructions are the vast majority. They contain fields for 3 registers, as well as a payload, which is used to store the ALU function code. I-type is immediate type instruction. This has a 9-bit sign extended offset, as well as the register that will read and write from. The J-type instruction is a jump type instruction, and it contains a 12-bit sign extended offset. My opcodes are 4 bits, so this gives me space for 15 different instructions. All of them are used except for F. The assembler implements a number of pseudo instructions that make things a little bit easier for the developer. And the ALU implements 8 different function codes. Those are add, or, and, subtract, shift, increment, invert b minus 1, and invert b plus 1. My assembler and emulator are both written in Java. They're actually part of the same Java package. So for example, the memory object in the emulator is also used by the assembler to generate the MIF file. The emulator supports a number of interesting options. For example, you can preload the input buffer with this stdn option. You can step through individual instructions or log the steps into a file. There's pretty extensive test coverage on both unit testing with JUnit covering about 100 unit tests, as well as system testing with a framework called BATS. This is a bash scripting language-based test framework that lets you run arbitrary programs and check their output. So I use this to assemble and execute all of the sample programs from problem set 4 inside the emulator and check the results. When you're stepping through instructions in the emulator, you get this really cool table that tells you the disassembled instruction. It gives you the value of the PC and IR. You can see all of the values on the stack. You can see all of the different register values, and whenever one of the register changes, you get this asterisk next to the name that indicates that the value changed. The hardware that my processor is implemented on is the Altera DE270. I found it really useful during the development process, especially when implementing all the instructions in VHDL, to utilize a number of switches and buttons and the various hex displays on the board to help debug my programs. The 2 blinking red LED lights are showing the state of the main finite state machine. The green ones are showing the state of the memory finite machine. The 2 banks of 4 hex displays here are configurable based on the switches below. This left hex display here is controlled by these 5 switches here, which I'm calling the debug switches. It's currently showing the instruction register. I can also show the current PC value. With various other settings, I can show the ALU in and out, register array in and out, and some other ALU function code and so forth. These three here are showing me the register in the right hand 4 hex displays. So this is register 0, register 1, register 2, and this is register 3. These 5 switches here are set for the clock divide, so it's currently set quite slow. These are setting the 5 high order bits of the clock divide. If I set these to 0, you'll see that everything is going full speed. This is the clock hold line, and I can manually step with key 2. This is the memory suspend line, and this is configured for memory set. The special feature for my architecture is a load feedback shift register. This is a way to get pseudo-random numbers inside your FPGA. I had always thought that getting random numbers was somewhat difficult. When you're looking at, for example, Linux system, dev random is based off of entropy received from various your keyboard and disk devices and network cards, and there's really complex algorithms involved. But an LFSR is like a poor man's way to get random numbers. So it's not truly random, it's a defined sequence, but it appears random to humans. So it's created by picking a specific number of taps, and you XOR the bits and those positions together. So if you take a look at this 8-bit value on the screen, I've picked the taps 7, 5, and 1, which are 0, XOR 0, XOR 1, and of course this gives us a 1 value, and we shift the register left and place that in the least significant bit position. If we do that again, our taps are now 1, 1, and 1. XORed together, those are 0. We shift left, and we get a 0 again. What's interesting is optimal picking of taps, like I have in my architecture, can result in a maximum sequence. So the maximum sequence for 16 bits is 2 to the power of n minus 1, or 65,535. The reason that it's minus 1 is because you're missing 0 from the maximum sequence. Otherwise, the shift bit would always be 0, and the sequence would eventually stop and be 0 forever. So this is the block diagram for my architecture. I don't have time to go into detail about all of it, but I will point out a couple of interesting aspects. The first is the stack pointer register, which takes as its input its output plus minus 1 or 1, depending on whether we are in a pop or a push situation. So this lets us increment or decrement the stack pointer. To the left of that is the load feedback shift register. You'll notice, interestingly, that there are no enable lines, and this is intentional. So the LFSR is, of course, clocked, like everything in the architecture, and on every clock cycle, the LFSR is updated. This, because of the memory accesses and memory mapped I/O take indeterminate amounts of time, this makes it less likely that you'll be able to predict where exactly in the sequence we are. So it improves the quality of the random numbers that we're generating. The first program I'm going to demonstrate is the final project assignment to multiply 2 integers together. So I've already gone ahead and loaded the MIF file into the board. I can swap over to the serial console and hit reset. It's going to prompt us to enter 2 integers and show us the product. So let's do a few examples. 12 times 12 is 144, minus 12 times 12 is minus 144, minus 12 times minus 12 is positive 144. You can also try a few things at the top of the ranges, like 32,768 times 1, we get the correct result. 32,767 times 1, and we get the correct result. It's worth noting that I don't have a hardware multiplier in my architecture. My special feature was the load feedback shift register, which I'll demonstrate next. But multiplication is performed using a subroutine that I've written that's using an efficient shifting and adding approach. The second program I'm going to demonstrate uses my special feature, the load feedback shift register. It's just a simple program that's going to generate lottery numbers for various different games. So when the program first loads, it's going to prompt you for a selection of Mega Millions, Powerball, or Mass Cash. So if I press 1, I'm going to get a Mega Millions number. If I press 2, I'm going to get a Powerball number. If If I hit 3, I'm going to get a mask cache number. There's a few interesting things to point out about this program. The first being that in order to adhere to the constraints of the particular games, we need to be able to generate numbers within a particular range. So, for example, for Mega Millions, the first 5 numbers need to be from 1 to 75, and then the second, or the last bonus number, needs to be from 1 to 15. So I've written a subroutine called RandBetween that grabs the value from the LFSR and then does modulo division to ensure that the result is within that particular range. The second constraint we have to adhere to is there can't be any duplicates within the first 5 numbers in Mega Millions. So there's another subroutine that checks all of the numbers generated so far to ensure that we don't have any duplicates. If there are, then it gets another number. And then the last little feature I have is just for presentation purposes, but I use a bubble sort to sort the first 5 numbers for Mega Millions and Powerball and all of the numbers from mask cache.